So in today's lecture, part two, ocean basins, we're now going to show you how the bathymetry data we have and some of the other data we have looked at in the past gives us a clear, comprehensive picture of the makeup of the world's ocean basins. So broadly, broadly speaking, oceans could be divided into one of three sort of provinces. You have your margins. This is where your ocean and continent are kind of like coming together. You have your mid-ocean ridges where the fresh ocean crust is being extruded. Then you have your abyssal plain and all the features that are present there. So we're going to start with describing continental margins and primary landforms. Then we're going to focus on mid-ocean ridges and how what happens in the mid-ocean ridges affects the shape of the ocean basin. Finally, moving into the greater ocean basin, and then in the next part of the lecture, sediment flux. So generally what you have at so generally right along the coastline, you're transitioning from continental crust to oceanic crust. The oceanic crust being marked with sort of your black marker here, and the continental crust being marked with red. And so you have a number of faulting. Now you hardly ever see this because we live on a planet with an active hydrologic cycle and a very heavy weathering rate for as far as things go. And all that sediment that is eroded off the continent, most of it gets deposited not that far away in this large deposit that can be, believe it or not, up to 20 kilometers thick, called the Continental Shelf. So generally the ocean doesn't get particularly deep for the first few anywhere between few miles and tens of miles, in a few places 100 miles offshore. Then you get to a place where it starts to get a little steeper. Usually this point corresponds to a spot that was probably the lowest low stand of sea level in sort of recent geologic time, accounting for land moving up and down. And below this, you have the continental slope. This is sort of that limit as to how far sediment, most sediment, get transported. And it'll generally be a little steeper. In some places, it'll just be about this steep. It will not look steep, but it'll keep going and going and going and going. Some places it does actually have a slope of up to about 30 degrees. That may not sound steep, but in terms of seafloor features on a large scale, it is. Now through this continental shelf, you often get canyons, usually during the low stands of sea level low periods. A little bit of erosion, a combination of erosion, landslides, river action will slowly but surely carve out vast canyons into the continental shelf. Now, to give you a sense of the scale of these, this Monterey Canyon, one of the more spectacular examples on the U.S. West Coast, is comparable in depth to the Grand Canyon on the Colorado Plateau. And on the East Coast, you also see things like the Hudson Canyon. Now, these things continue to transport submarine landslides, submarine debris flows, and all of this stuff that has been sloughed off the continent gets deposited, most of it gets deposited near the toe of the continental slope, creating this sort of gently sloping feature of sediment sloughed off the continent called the Continental Rise. Here in San Diego, we have a couple areas where this feature is somewhat preserved in the sediment record. You take a look at this map of sediment thickness just to get a sense of how thick the deposits on the continental shelf are. Pay close attention to this scale bar. Notice the areas, especially at the mouth of the Ganges, Brahmaputra rivers and the just north of the Amazon River mouth, and in much of the western Gulf of Mexico, along the North American East Coast, these very thick packets of sediment. Ask yourself what kind of tectonic boundary is most associated with this. Yeah. If you notice that if you remember the Mid-Atlantic Ridge and the fact that this is an opening ocean basin, remember correctly. And You want to compare this to what you see over here on the Pacific coast, where we have primarily convergent plate boundaries in the Pacific Basin. Anyway, what's happening here? Why is it that we don't have thicker packets of sediments at the convergent boundaries? Well, there are at least two different classes of margins. Let's take a moment, compare the east coast of the USA with the Chile on the west coast. Both are sort of margin environments. Which one has the thicker continental shelf? Which one has the deeper, weirder submarine canyons? And these are both should be at about the same scale. Not perfectly so, but yeah. Which one has bigger mountains on the land surface? It's funny. You'd think generally high mountains would generally give you more runoff and more erosion, more sediment. Where is that sediment going? Why do you have so much thick sediment in a place that has basically relatively low relief on the land surface where the sediment source? This is because you have two different types of margins, at least two. We're just going to look at two because everything else beyond the kind of scope of this course. We have your passive continental margins. You see this in much of the Atlantic Basin, where the last major tectonic event was the opening of a mid-ocean ridge. And by the way, I do not like this diagram because I'll explain that sometime if you get to meet me. I don't like the fact that the distance from here to here is shorter than the distance from here to here. I do not like that at all. And then you have your active margin. These are associated with convergent plate boundaries and transform plate boundaries. Now, in your passive margins, you typically see large continental shelves, gentle continental rises, and fairly evenly spaced submarine canyons that aren't particularly large. Whereas in your active margins, you're often seeing very steep mountains rise up not far from the coastline. You're seeing trenches, and this actually is probably where most of the sediment is disappearing. You can see it very clearly here in this diagram where we have this active margin in the trench. A lot of the sediment's coming off the continent gets trapped in this trench. This also tends to leave the seafloor substantially less sediment covered seaward of an active margin. And not only sediment just sort of getting stuck in this trench, a lot of that's going back down into the trench and powering the volcanism. What takes place at active margins can get pretty darn intense, actually, because with all the subduction, all this cold material, all this new material being brought into the mantle, reacting with it, creating new lavas, and also the metamorphism of rocks at greater depth along the subducting slab, you can get some and also the horizontal transport of all this sediment on the seafloor creates all these interesting features at active margin. So you usually have a trench. You often also get an outer trench high because you can't bend something downwards without some part of it flexing upwards. And depending on what's happening, sometimes you'll get a very shallow angle of subduction. The volcanoes will pop up very far inland. Sometimes you get a very steep angle of subduction, and the volcanoes will get closer and closer shore. The subduction is especially steep. Sometimes the subduction will actually literally drag apart the overriding plates and create a little back arc spreading center behind the main arc. This will generally be an environment that's getting a lot less sediment, and you'll see quite a bit of this will be a great place for coral reefs and other interesting features. For the next segment, we're going to look at mid-ocean bridges. Thank you very much for your attention, and enjoy.